Hello math friends, this is section 4.9 day 2 notes for AP Calculus. The second part of section 4.9 is just applications of antiderivatives. So we're just going to jump right in knowing that, whatever we're doing here, we're probably going to have to find antiderivatives of functions. So example 1 is a particle problem. It says a particle moves with acceleration function a of t equals 5 plus 4t minus 2t squared. So we are given acceleration, which we know is the second derivative of position and is the first derivative of velocity. Its initial velocity is v of 0 equals 3 meters per second. There's an initial condition that will help us solve for c. And its initial displacement is s of 0 equals 10. There is an initial condition that will help us solve for c in our position function. Find its position after t seconds. All right, so we're going to have to do two antiderivatives because, again, we are given acceleration, and we are asked to find position. So first we have to find the antiderivative of acceleration, which would be velocity. Then we have to find the antiderivative of velocity, which would be position. All right, so step 1. We are going to use a of t and the given initial condition v of 0 equals 3 meters per second to find the velocity function. So I'm going to start with a of t. A of t is negative 2t squared plus 4t plus 5. So I know I have to find the antiderivative of this function, which is going to be my v of t. So v of t is going to be equal to, let's see, the first term will become t cubed. I will have to multiply by 1/3, and don't forget the negative 2 that was already there. My second term will become t squared, so I'll have to multiply by 1/2, and don't forget the 4 that was already there. And my third term will become 5t, and then I will have a constant term of c. So let's clean this up, and then let's check it, and then we'll solve for c. So negative 2 times 1/3 is negative 2/3 t cubed. 4 times 1/2 is 2t squared. Plus 5t plus c. So if I check my terms, the first term, if I brought down the 3 times negative 2/3 would just be negative 2t squared. Check. Second term, if I brought down the 2 times 2 would be 4t. Check. Third term, derivative of 5t would be 5. Check. Fourth term, derivative of a constant would have been 0. Check. Okay, so that looks good. Now let's solve for c. We know that v of 0 is 3. So 3 should be equal to what I get when I plug in 0 for t in my velocity function. And every term that I plug 0 into just cancels out, so that tells me that c is 3. So my velocity function, my v of t, is equal to negative 2/3 t cubed plus 2t squared plus 5t plus 3. Okay, so that was my step 1. Now my step 2 is I have to use my v of t and the initial condition for position that they gave me to find the position function after t seconds. So step 2. Use v of t and s of 0 equals 10 meters to find a position function after t seconds. Okay, so let's begin with what our v of t was again. Our v of t was negative 2/3 t cubed plus 2t squared plus 5t plus 3. So my s of t is going to be, this term will become t to the 4th. I need the 1/4 to undo it in the front, and then I still need the negative 2/3. The second term will become t cubed. I need a 1/3 in front to undo that, and I still need the 2 there. The third term will become a t squared, so I need a 1/2 plus the 5 that was already there. And the 3 will become a 3t, and then I'm going to need a plus c. Let's simplify this, and then we'll check it. So negative 2 over 12 is going to become negative 1/6 t to the 4th, plus 2 times 1/3 is 2/3 t cubed, plus 5 times 1/2 is 5/2 t squared, plus 3t plus c. Okay, checking each term quickly. If I differentiate negative 1/6 t to the 4th, if I brought down the 4, negative 4/6 would be negative 2/3 t cubed. Check. If I brought down the 3 times 2/3 would just be 2 t squared. Check. Checking the third term, if I brought down the 2 times 5/2 would just be 5t. Check. If I differentiate 3t, I get 3. Check. And if I differentiate c, I get 0. Okay, so now let's find our c value, because s of 0 was 10. So that means that 10 has to be equal to, and again, when I plug in 0, everything goes to 0, right? So gone, 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 gone. I find out that c is 10. So my position function is s of t equals negative 1/6 t to the 4th plus 2/3 t cubed plus 5/2 t squared plus 3t plus 10. And there is the answer to example 1. In example 2, a stone is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. Part A, find the distance of the stone above ground level at time t. All right, so let's start with that. If we are given the fact that this stone is being dropped from 450 meters above the ground, okay, we know that that's an initial position. So I'm just going to jot down some information right here. This right here tells me that s of 0, my position function, is 450. I'm going to need that later at some point, okay? And if it's dropped, this also tells me that it's released with 0 velocity, right? We're not throwing the rock down, we're just simply like letting it go, and it's falling of its own gravitational pull towards the ground, right? So this means that it's being released with an initial velocity of 0. So v of 0 is 0. That's going to help us find c for our velocity function. What they don't give us in this problem, prerequisite knowledge that we definitely need, that they don't tell us, so I'm telling you right now, is that acceleration of a falling object is negative 9.8 meters per second squared. Okay, so they don't give us the acceleration function. We just had to kind of be able to figure that out for ourselves. So for part A, if we want to find the distance of the stone above ground level at time t, then we have to find 2 antiderivatives. So we start with the fact that our acceleration function is negative 9.8 meters per second squared. Okay, so the derivative, or the antiderivative of that would be our velocity. So our v of t would just be negative 9.8 t plus c, right? But we know that v of 0 is 0, right? The initial velocity is 0 because the stone is just dropped. It's not thrown. So 0 would be equal to negative 9.8 times 0 plus c, which tells us that our c value is 0. So that means that our velocity function is just negative 9.8 t. That's pretty easy. And so now we need our position function, which is going to be the derivative of the velocity. So then our s of t is going to be negative 9.8. Now, if we're going to change this to t squared, we have to multiply by 1/2. And again, we didn't have a constant term, so we're going to have a plus c here, which we will have to solve for. So half of negative 9.8 is negative 4.9 t squared. And again, this c right here, this is our initial position, which we circled above in orange and said S of 0 is 450. So 450 is what we get when we plug in 9.8 divided by 2, negative 9.8 divided by 2 is negative 4.9 t squared. But t is 0. Sorry, we're solving for c. So that tells us that c is 450. So the answer to part A is S of t is equal to negative 4.9 t squared plus 450 meters. Okay, so there is our position function. Part B of this problem says, how long does it take the stone to reach the ground? Okay, well, keep in mind the stone is on the ground when its height is 0. So since we have a position function, our S of t is our position function, letter B is really asking us, when does S of t equal 0, or how many seconds does it take for the stone to be at ground level? So if we set that equation equal to 0, 0 equals negative 4.9 t squared plus 450. And if we solve, we would get negative 450 equals negative 4.9 t squared. Divide both sides by 4.9. We get t squared equals 91.837. And of course, when we square root that, we're going to get two answers, the plus and the minus. But if we're talking about time, only the positive answer makes sense here. When we square root both sides, we get t equals 9.583 seconds. So that is the answer to part B. Part C asks us, with what velocity does it strike the ground? Well, we just found out how long it takes the stone to hit the ground. It takes 9.583 seconds. Since we already have a function for velocity, here's our velocity function right here. For part C, we just need to find v of 9.583, which is equal to negative 9.8 times 9.583. And when you plug that into your calculator, you get negative 93.915 meters per second. So that is the velocity with which the stone strikes the ground. Part D of example 2 asks us to now think about, what if the stone was thrown downward with a speed of 5 meters per second instead of just dropped? Well, obviously, if the stone is being thrown, that is going to change our velocity. So for letter D, if the stone is thrown downward, then our initial velocity would be that speed of 5 meters per second. Now, if it's being thrown downward, then v of 0 would be negative 5 meters per second, again, because it's going down. Okay, so that's going to change our v of t function, right? Then our v of t function, instead of just being negative 9.8 t plus 0 when our initial velocity was 0, now our v of t is going to be negative 9.8 t minus 5. And how is that going to change our s of t? Well, then our s of t is going to be negative. Now, again, we're finding the antiderivative here. So this term will be negative 4.9 t squared, right? Because multiplying negative 9.8 by 1/2. And then this term is going to be negative 5t. And we're not changing our initial position. It's still 450 450 meters above the ground. So that's still going to be 450. So now, if this is our new position function, if the stone is being thrown down there, then the stone reaches the ground when S of t equals 0. So if I take that position function and I set it equal to 0, that'll tell me the time that it takes for the stone to hit the ground. So 0 equals negative 4.9 t squared minus 5t plus 450. This is not factorable, so we are going to solve by the quadratic formula. So t will be equal to the opposite of b, so positive 5, plus or minus the square root of negative 5 squared plus negative 4 times a, which is negative 4.9, times c, which is 450, all divided by 2 times a, which is negative 4.9. And then you grab your calculator. And the 5 minus is going to give you a negative, well, actually, the 5 plus is going to give you a negative value because you're going to be dividing by negative 9.8 in the denominator. But as you know, you're going to get two answers, one positive and one negative. Only the positive answer makes sense here because we're talking about time. And so if you do your calculations correctly, you should get t equals 9.087 seconds. Okay? So interesting, in part B, the stone hit the ground when it was dropped after 9.583 seconds. And in part D, the stone hit the ground when it was thrown downward after 9.087 seconds. So really only a difference of about a half of a second between the stone being dropped and the stone being thrown. We're going to change gears a little bit now, and we're going to talk about slope direction fields. Now, slope direction fields are still an application of antiderivatives, but basically the idea here is that you can use a sketch of a slope direction field to help us sketch what a graph of an antiderivative would look like. Recall that if capital F is the antiderivative of f, then the y values from f would have been the slopes on capital F for any given value, right? That relationship between a function and its derivative is that the slopes on the function are the y values on the derivative. Therefore, the y values on the function are the slopes on the antiderivative, right? It goes both ways. So for our last example, they give us this function, f of x equals the square root of 1 plus x squared plus x. They want us to sketch the graph of the antiderivative that satisfies the initial condition f of 0 equals 0. So that f of 0 equals 0 right there, that tells us a point on the curve so that we know where this graph has to pass through. And so when we sketch our graph using our slope direction field, we're going to kind of use that point as a starting point. So basically, what we need to know is a table of values for this function f of x. So that's the first thing that I'm going to do is I'm going to build a table of values for x and f of x. And I want to make a fairly big table because I want a lot of slopes so that I have a more accurate picture of what my graph should look like. So I'm probably going to do x values from -5 all the way up to +5. Okay, and again, I am just plugging these x values right into f of x, doing the math. We have a square root in our function, so these aren't going to be very nice numbers. So when you plug in -5, we get 0.09. When we plug in -4, we get 0.12. When we plug in -3, we get 0.16. When we plug in -2, we get 0.23. When we plug in -1, we get 0.41. When we plug in 0, we get 1. When we plug in 2, we get 4.24. When we plug in 2, oh, sorry, I skipped one. My apologies. Back up for a second. When we plug in 1, we get 2.41. When we plug in 2, we get 4.24. When we plug in 3, we get 6.16. When we plug in 4, we get 8.12. And then finally, when we plug in 5, we get 10.1. Okay? So these y values on f of x are going to be our slopes on our antiderivative big F. Okay? So now we're going to do something called sketching a slope field. So you're going to draw yourself a nice coordinate plane. Use as much of the space as you have there in your white space on your paper, and we're definitely going to go higher on the y-axis than lower, so we'll put our x-axis down here. And we're going to count out to +5 and -5. And we also need some tick marks on our y-axis because we're going to kind of be approximating little slope lines, so we kind of need an idea of how steep things are. And notice we did have a slope, or we did have a y value of 10, which means that at the end we're going to have a slope of 10, which is pretty steep. Okay? And so now I am just going to use my table, and I'm going to move across my graph. Now this is not an exact science, so I don't want you to stress out too much about this, but you're just going to try to make little line segments that represent the slope at that particular x value. So when we're looking at our table, the slope at -5 was 0.09, right? So not even 0.1. So that slope is positive, but really close to 0. So if I were to sketch a slope field at x equals -5, I'd be drawing slopes that were positive, but were almost horizontal, right? And we're just going to do it in a vertical line at x equals -5. We're going to have those slopes that are, they look like they're almost horizontal, but not quite, right? Slightly positive. Then when x is -4, my slope is ever so much bigger, just the teensiest, tiniest bit, right? So these lines aren't going to look that much different than each other, to be honest. They're going to be pretty similar. Positive, but very close to 0. Very shallow slopes. When x is -3, I'm at a slope of about 0.15, so again, just slightly bigger. And again, sometimes these are so hard to sketch because you want to make them look different, but how can you make a slope of 0.1 and 0.15 look that much different when they're so close together in numerical value? Then at -2, I'm at about 0.25, I'm at about 0.25-ish, so slightly more positive, but again, still shallow. A slope of 0.25 is like a slope of 1/4, so pretty shallow as far as slopes are concerned. At -1, I'm at about 0.4, so almost 1/2. So a little bit steeper. And then at x equals 0, I'm at a slope of 1. So up 1, right 1. Slope of 1 looks like about like that. That's why the lines on the y-axis kind of help us figure out how steep our lines should be. And then I'm at a slope of 2.5. So again, you can kind of go like up 2.5, right 1. What does that look like slope-wise? Looks kind of like that. And then I'm at a slope of 4.24. So I'm getting pretty steep pretty quick. And then at x equals 3, 6. And again, now we're going to struggle to make the lines look more steep as we go because we get to a certain point where it almost looks vertical. And then we're at a slope of 8. So just do your best to try to make it look like you're getting steeper and steeper. And then we're finally at a slope of 10. Okay? So you can kind of see that obviously as we move across the graph from left to right, you can see that the slope of our curve is going to be increasing, right? So this graph's slope is going to be increasing at an increasing rate when we think about, the language of calculus. And so now if we actually want to use this slope field to draw our curve, we go back to the fact that they told us that f of 0 equals 0. So that's a point right here. So we know that our graph has to pass through that point. And then from here, we just do our best to sketch the curve following the lines that we've drawn in our slope field. All right, so getting more and more steep as we go, like so. And then on this side, following the lines of our slope field, like that. Okay, so that right there is a guess using a slope direction field at what the antiderivative that passes through the point 0, 0 for that function f of x would look like.